in and thinking, oh, dynamics, we did dynamics last week. I'm not going to watch this. That's right, we're moving on to centripetal motion, which is going to have something to do with dynamics. You know, we expect to see a lot of these ideas as we work with them. We'll show up again later in future topics, but we're kind of building on them and looking at what the new stuff is as we sort of get more elaborate with our formulae. That being said, I'm also just going to double check to make sure I've got good audio when nothing is sounding weird, so I'm going to listen to it on the phone. Okay, I can hear myself talking. That is definitely going to throw me off, so we're going to turn that off. That being said, audio sounds pretty good. I think we're ready to jump into this. So, as always, we're just going to be going through. We'll take a look at some of these ideas generally, but then we're going to be looking at some multiple choice problems and then some FRQs. As always, we have the chat window up to my left here. If you see me turning this way, this is to check on that or to check on anything about the health of the stream. Maybe if the audio is going weird or internet's being goofy, you know, who knows? As if you have any questions as we go, feel free to type out a question in chat. If I hear the notification, I'll look and we'll discuss what's going on. Hopefully answer your questions, make things easier. That being said, let's get into it. So we have for our lovely little splash screen here, actually kind of touches on the main idea of centripetal motion. And so this is a separate topic from rotational motion. Rotational is going to be once we start incorporating our Greek terms, such as theta, omega, and alpha. For what it's worth, these can be found to do with a corollary to our linear motion, our linear motion quantities, which would be position or arc length, velocity, and acceleration. That being said, these aren't going to come up in this unit. That comes up with torque and rotational, which is actually the last unit that's going to be tested this year on the AP Physics 1 test. We've already talked about how there used to be electrostatics, DC circuits, mechanical waves, and sound, but those three topics have been pulled this year. I believe they're going to be a part of the AP Physics 2 curriculum. Yeah, lots of changes this year, especially just because of the way that students have had to learn in this past year has been a little bit unfair. So they decided to nerf the exam a little bit. So that being said, the relation we're looking for in centripetal motion is this guy. Our centripetal force is going to equal mv squared over r. If you only can remember one thing from today, it's probably going to be this guy. This comes from using our centripetal acceleration as v squared over r, and then this is just m times a. Now a centripetal acceleration is going to be a change in the tangential velocity. Tangential having the word tangent in it. So our velocity is running a tangent. It is touching the circle at one point and then moving on. And as we go around the circle, we have a tangential velocity at each point. And if we're traveling the same speed, this has the same magnitude, but velocity has two components, right? This is a vector quantity, so it has both magnitude and direction. And as we're rotating, our direction is changing. And so as our direction is constantly changing, we're constantly accelerating in circular motion. We're not going to do that tutoring opportunity right now. And so that type of circular motion is always going to be pointing radially inward. So for our context, that means we can define the force that's pointing radially inwards as the centripetal force. And we have to be a little bit careful here because this is the net force inward. We'll write this as F net inward. And so this could mean in the context of, say, an object in orbit, that would be just gravity. But if we had, say, an object being pulled on a string, swung around in a circle, but in a vertical circle, our net force inward would be different based on where it's at in the circle. At the top, we would have a tension force and a gravity force helping us out. So then our Fc would be some tension plus gravity. But at the bottom, our gravity would be pointing in the opposite direction. If we had our tension force pulling radially inwards, but our gravity pulling radially outwards, it's still on the same axis as the radial direction. But we would then write this as the force of tension being the positive one pointing inwards minus the force of gravity pointing radially outwards. Same axis, different direction, introduce a negative sign. Similar to topics we've seen in the past. Yeah, so I guess that being said, why don't we just jump into some problems? Oh yeah, and okay, we will also be covering gravitation. This comes up quite nicely in this unit because we can relate this to a centripetal force very well. But we've seen gravitational force, just Fg equals mg, right? Well, wrong, actually. This works, but this is just an approximation. This works well for when we are near the surface of the Earth. But as we move further away, we expect gravity to have some sort of dependence based on how close we are. And so we write this force for larger scales, kind of once we start getting to heights comparable to the radius of the Earth, or significant relative to the radius of the Earth, so it can still be small, but not negligible. This we use as a capital G, capital M, this is the mass of the large object that we are orbiting, times a little m, this is the mass of the object that is orbiting, divided by the radius squared, which is the radius between their centers of mass. And so for circular motion, we can then say that this is a centripetal force because in space, when we're in orbit, this is the only force that's pointing radially inwards. And so we'll see this relation come up in the problems that we'll do today. So that being said, let's get started. Alrighty, so right off the bat with some circular motion multiple choice, we've got a multiple correct option here. A person standing on a merry-go-round which is rotating at a constant angular speed. Angular speed being the rate of change of the angle per second. The tangential velocity depends on the radius. Further out we go, the larger the circle we're tracing out, so higher circumference in the same amount of time, larger velocity. Angular speed doesn't change though because the angle that's traced out is going to be constant at any radius. Which of the following are true about the frictional force exerted on the person by the merry-go-round? The force is greater in magnitude than the frictional force exerted on the person of the merry-go-round? That's the same force. It can't be greater in magnitude, so we can rule out A. The force is opposite in direction to the force exerted on the merry-go-round by the person. Yes, this is going to be true. This is due to Newton's third law. They're third law pairs. They have equal and opposite reactions. Notice how this is force exerted on the merry-go-round by the person, not on the person by the merry-go-round. So we have that flipped behavior is why we get that opposite direction. The force is directed away from the center of the merry-go-round. Now this is a little bit tricky because if we think about our merry-go-round from a top-down perspective, we've got our little guy here. And this would be our axis of rotation. As we're rotating around, our guy would just move in a straight line unless he were held in place by some centripetal force to make him trace out this circle. These visible? Okay, these are all visible. I won't go too far over to the right here, but that's fine. And so the force pulling him inwards is that frictional force. So that means the force is acting radially inwards. And so it is not directed away from the center of the merry-go-round. So that means kind of by default D has to be true. But let's just have a look at it. The force is dependent on the person's mass. Yes, we expect that to be true because friction force is going to equal mu times Fn. And in this case, we would expect Fn to equal Fg, which would then give us mu times mg. Look at that. It depends on the mass. So D is also true. Cool. So number 2, we've got a ball attached to a string is whirled around in a horizontal circle having a radius r. The radius of the circle is changed to 4r, and the same centripetal force is applied by the string. The new speed of the ball is which of the following? So we have the same centripetal force. In the first case was just mv squared over r. Next, the radius is going to be changed to 4r for the same centripetal force. So we can set that equal to this, but now we have an m, we'll call this v prime. That's our new velocity. And our new r will be 4r. And so we want to solve this for v in our new v in terms of our old v. So we can cancel out our m's, we can cancel out our r's, and then we'll multiply by 4, and then we'll take the square root. And so we have 4v squared is equal to our new velocity squared. So we're traveling at, wait, is that right? Yeah, no, that should be right. Yeah. So same centripetal force, larger radius, higher velocity. And then we take the square root. This includes the square root of this 4. So we actually see then our v prime is going to be double our v. That's going to be b. Ooh, no, sorry, not b. That's going to be d, twice the original speed. Cool. Any questions so far? Looks good? Looks good. Okay, yeah, no, I guess that's fine. So that seems a little bit iffy there, but I trust the math. Next, we've got a racing car is moving around the circular track of 300 meters as shown above. The instant when the car's velocity is directed due east, its acceleration is due south and has a magnitude of 3 meters per second squared. So its velocity is due east, and if its acceleration is due south, acceleration is radially inwards, so east would be here. Acceleration going south like that, so we're going clockwise. So we can rule out C and D. And the instance when the car velocity is due, and the velocity has a magnitude of 3 meters per second. Oh, no, the acceleration has a magnitude of 3 meters per second. So A equals v squared over r. Let's get our velocity at, that's going to be the square root of a times r, which is, in this case, the square root of 900, which is going to be 30. So that is A, clockwise at 30 meters per second. 4, we've got a penny on a turntable, rotating at a constant rate, moves counterclockwise in circles shown above. Which of the following best represents the frictional force exerted on the coin at this position? Well, it's like we saw before. We expect the frictional force to be pointing radially inwards, because that's what's giving us the centripetal motion. If we're at the top, we expect the pointing inwards to be pointing down. So C is our best option here. In fact, yeah, C is the only correct option there. 5, in which of the following situations would an object be accelerated? Select 2 answers. Moves in a straight line at a constant speed. That is not acceleration. Acceleration would be a change in velocity. So constant speed, no change. Straight line, no change. An object moves with uniform circular motion. Yep, that is accelerating. Even if it's not changing the magnitude of the velocity or its speed, uniform circular motion means we're constantly changing direction. So if we're changing directions, we're changing velocities. If we're changing velocities, it means we're accelerating. So B is going to be one of our cases. C, it travels as a projectile in a gravitational field with negligible air resistance. Yeah, that's also going to be true. We'll be accelerating due to gravity, moving downwards, like that kind of projectile arc that we saw back when we were doing kinematics. That was like a week ago now. And then it is at rest. No, we expect it. We can't be at rest and accelerating. That's not true. So that gives us with just B and C here. All right. Incidentally, the multiple choice has been split up into, we've got some circular motion stuff and some gravitational stuff. So you're going to see these are going to start to jump around a little bit in numbers. But in this case, it looks like this one did follow directly from us. Cool. Next, we've got an automobile moves at a constant speed down one hill and up another hill along the smoothly curved surface shown above. Which of the following diagrams best represents the directions of the velocity and the acceleration of the automobile at its lowest position? So we're kind of tracing out like a little bit of a circle here, right? So if we're moving in circular motion, our acceleration is going this way. And then our tangential velocity will be moving at the tangent. So our acceleration is going to point up and our velocity is pointing to the right. That's going to be B. 7, we've got a car initially travels north and then turns to the left along a circular curve. This causes a package on the seat of the car to slide towards the right side of the car. Which of the following is true for the net force on the package while it is sliding? So, if the package had enough frictional force, it would stay seated. Oh, okay, so that's actually, I didn't read our options here. This is, our options would be not enough force directed in one of the directions, so that would be towards the center of the circle. Would that be north? If it's traveling north and turning left, no, we would want the force not diverted north, but to the center of the circle. Not in the tangential direction, and we wouldn't expect the force to be directed away. No, we wouldn't expect the force to be directed away. There's a net force probably still pointing inwards, but it's not enough force directed towards the center of the circle, and so the package slides. 8, we have a child that has a toy tied to the end of a string and whirls the toy at a constant speed until they wrap it around their neck, and it all ends in tears. You don't give your child a bolo. They're very dangerous. They whirl the toy at a constant speed in the horizontal circular path of a radius r. The toy completes each revolution of its motion in a time period t. What's the magnitude of the acceleration of this toy? Well, our acceleration is a vertical, no, it's a circular path. So it's v squared over r. But we also know our velocity. Well, velocity is distance over time, right? Or displacement over time if we want to be picky about it. But if we so the magnitude is just going to be distance over time. And the magnitude for a rotation would be we travel an entire circumference every period. Our distance is a c, 2 pi r, and our period is a capital T period. So we can plug that in here, giving our acceleration as 2 pi r over t squared over r. Canceling one of the r's up here, giving us a 4 pi squared over t squared r, which is B. Look at that. Good. Next we've got, last one for this page here, a compressed spring mounted on a disc can project a small ball. Project like launch like a projectile, or project like a movie projector. There's a lot of old school terminology here. When the disc is not rotating, as shown in the top above, the ball moves radially outwards. The disc then rotates in a counterclockwise direction from above, and the ball is projected outward at the instant the disc is in the position shown above. Which of the following best shows the subsequent path of the ball relative to the ground? So we don't expect it to be A, because if we're rotating this way and the ball wants to move this way relative to this, it's got some upwards velocity at this instant, so it's not going to curve down. That's just not going to happen. So we can rule out A. B looks promising. B has this kind of curved motion that's moving up in the direction of our two net velocities. But B is curved though. And so if we compare this to something like D, we see D is going to be more accurate, because as soon as we are free of the disk, it's not going to be influencing our velocity anymore. So it can't actually curve our velocity that starts out horizontal and curve it up like it will in B. C just has us shoot right out, but that ignores the upwards component for our velocity, which we need to factor in. So then that leaves us with D. Oh, business calculus. No, I'm not going to teach you business calculus. Sorry. Perhaps someone, if you make me a good enough offer, I'll teach you business calculus. But generally, you don't need calculus or business. Just hire a mathematician. Hire all mathematicians. They're better at math. So next we've got a centripetal force of 5 newtons is applied to a rubber stopper moving at a constant speed in a horizontal circle. If the same force is applied but the radius is made smaller, what happens to the speed and the frequency of the stopper? So we know the Fc is given as 5 newtons. That is going to be our mv squared over r. Same force is applied, but radius shrinks. Therefore, speed goes up. If speed goes up, this is going to increase the frequency because our angular frequency is 2 pi over t. Again, it's the same logic for the velocity, where it's the angle we travel per time. And for a complete cycle, we travel 2 pi radians. And then we can write this as 2 pi times f. And then omega is also directly proportional to v times r. So v goes up, omega goes up. If omega goes up, f goes up. V increases and f increases. That is A. Good, good. 25, we're told astronauts on the moon perform an experiment with a simple pendulum that is released from the horizontal position at rest. At the moment shown in the diagram, when theta is between 0 and 90 degrees, the total acceleration of the mass may be directed in which of the following ways? So we have some downwards acceleration on this mass at this point, right? That's what's driving us down here. There's a force pulling us in this way, but until we move, it's not going to actually pull us in until we then get past this, and then we reach that point where the tension applies. So then we come around here. Now the tension is taking a lot of the weight, but we still also have some net force downwards. That being said, this is making circular motion, so we expect the net force, therefore the net acceleration, to be pointing up and to the right, along the connecting string toward point P. That looks good. 26, we've got a 4 kilogram mass is attached to one end of a rope 2 meters long. If the mass is swung in a vertical circle from the free end of the rope, what is the tension at its highest point? So at its highest point, our centripetal force is the force of tension plus the force of gravity. So we get Fc is equal to Ft plus Fg, giving us that Ft has to equal Fc minus Fg. And in this case, that would be our centripetal force is mass times velocity squared over r, and our Fg is mg. Our mass was given as 4 kilograms, our velocity is 5, and our rope is 2 meters long. So we have 4 times 25, which is 100, divided by 2, so that's 50, minus 4 times 9.8, which they do use 9.8, so 19.6, no, not 19.6. 19.6 times 2. 4 times 9.8. 39.2. And so we get 50 minus 39.2, which is going to give us a tension of 10.8 newtons, not 50. A lot of people will probably think 50 because they'll think force of tension is equal to the centripetal force. But the centripetal force is the net force pointing in the radial direction. So we have to factor out this gravity force is taking the majority of the centripetal. It's doing most of the work. It's contributing 39 of the 50 newtons. And so only 10.8 is being contributed by the actual rope, which is good. That means, you can spin it faster with a weaker rope and it will still help. A ball of mass m is fastened to a string. The ball swings at a constant speed in a vertical circle of radius r. The other end of the string is held fixed. Neglecting air resistance, what is the difference between the string's tension at the bottom of the circle and at the top of the circle? Well, that's just going to be a difference in... So at the bottom of the circle, we expect the tension to equal the centripetal force plus the gravitational force. And at the top of the circle, we expect it to equal the centripetal force minus the gravitational force. So the difference is 2 times the gravitational force, which is m times g, which 2 times mg is b. Good, good, good. Guys having fun yet? I'm having fun. 28, we've got an object weighing 4 newtons, swings on the end of a string as a simple pendulum. At the bottom of the swing, the tension in the string is 6 newtons. What is the magnitude of the centripetal acceleration of the object at the bottom of the swing? So we know the tension and the weight. And so bottom of the string gives us Fc is equal to Ft minus Fg. Yep. And that's going to be, in this case, 6 newtons minus 4 newtons. Wait. Yeah, no, that's right. That's right. And so we expect 2 newtons to be equal to our mv squared over r. Do we have a radius? We don't have a radius. Because we don't need radius. We just need to divide by mass because we're looking for centripetal acceleration, and centripetal acceleration is v squared over r. Is that okay? We can still see that. Good. So we divide this by the mass, and then if the weight is 4 newtons, we can assume the mass is probably going to be, if we divide that by 10. Oh wait, they do it in terms of g. Really? In terms of g? Okay. So yeah, that's going to be half a g, because 4 newtons is 1 g. So yeah, that's just going to be a half there, which is a. Yeah, there's 2 newtons is half of 4 newtons, and 4 newtons equals mg. So this means m times our acceleration. This acceleration term has to equal half a g. All right, kind of running out of space here, but that's fine. If we do need more space, we'll just get a new one, get a new page. We've got riders in a carnival ride standing with their backs against the wall of a circular room of diameter 8 meters. The room is spinning horizontally about an axis through its center at a rate of 45 revolutions per minute, when the floor drops so that it no longer provides any support for the riders. It's a minimum coefficient of static friction between the wall and the rider required that the rider does not slide down the wall. Okay, yeah, let's get us a new page, just because that's an actual one we gotta write. Do we wanna make this like a graph paper? That's kind of fun, right? It's like an extra piece of scratch paper we've got. So we've got some sort of carnival ride. We've got some axis it's rotating around, and we've got people slammed up against the wall. And they're being held up by a force of friction, right? So they need a force of friction pulling upwards to overcome the gravitational force. And their normal force is pointing perpendicular to the wall. The normal force is going to be the centripetal force. So we need our normal force to equal our mass times our velocity squared over r. We need to convert our velocity into the revolutions per minute, or moreover, probably convert. So we had an omega was 45 revolutions per minute. Let's get that in terms of radians per second. So let's see. We have 45. We want revs per minute. We've got 2 pi radians per 1 revolution. we've got 1 minute per 60 seconds. There we go. So revolutions cancel with revolutions, minutes cancel with minutes. We're left with radians on top, seconds on bottom. So to get this in radians per second, that'll be 45 times 2 pi divided by 60, which is going to be 4.71 radians per second, or actually I like this version way better, 3/2 pi radians per second. And then to get this in terms of an actual velocity, v is equal to omega times r, which is going to be omega times our diameter over 2, because we are given our diameter, which is 8 meters, so diameter over 2 will be 4 meters. So we have 3/2 pi times 4 meters, meaning we trace out, we're going to be traveling at a tangential velocity of 18.85 meters per second. Is that still visible? Oh, that's a little not visible. Yeah, we just I'll write this down here then. This was just omega was equal to 45 revolutions per minute. Yeah, and I like that better. So we'll leave it like that instead of the 4.71, which is still good, but okay, we can't do that. It's not smartboard. That's fine. Good. And so let's see. So this lets us know then what the friction force has to be. Sorry, this lets us know what the normal force is going to be, because our because we're just going to divide by r, aren't we? Oh no, but we're going to square it, so it doesn't matter. So we expect a normal force when we're traveling of this to be, we'll still leave it because I don't believe we were told their mass. Let's have a look here. Yeah, this is going to be invariant of the rider's masses, because we want any riders to be able to ride this. And so our v squared is going to be 18.85 squared divided by our radius, which is 4 meters. So our normal force is going to be equal to, let's square this guy and then divide it by 4. Our normal force has to equal 88.8 m. So this is still in terms of our mass, right? 88.8 times our mass. So this is technically an acceleration, which is pretty fast. And so we now need to satisfy the condition that our frictional force is at least equal to the gravity, and at least equal to for the minimum case. And so that gives us mg must be equal to mu times our Fn. And our Fn we just defined as m times 88.8. We can now cancel out our m's, and we want to solve for mu, so we'll divide by 88.8. That is g divided by 88.8 equals mu. 9.8 divided by 88, it's going to be about 0.1. 9.8 divided by 88.8, it is 0.11. 0.11, which is B. Look at that. Very nice. Good. All right, let's move on. Okay, so now that was the last of the circular motion multiple choices. Went by pretty quickly. And now we're going to take a look at gravitational problems. And so in this case, we've got, we've shown 5 satellites make a circular orbit around an object that is much more massive than any of the satellites. The mass and orbital radius of each satellite are given below, even though they only give us 4. There's the 5th satellite that's just missing. Oh well. Which satellite has the greatest speed? Well, that's a good question. So speed is going to be related to a centripetal force, which is mv squared over r. So speed is the absolute value of v. But our centripetal force, when we're out in space and dealing with gravitation, is our gravity force, using big G gravity, gmm over r squared. So we want to take this relation and solve this for v. So we'll multiply both sides by r, and then we'll divide both sides by m, and then we'll take the square root, giving us v is equal to the square root of gm over r. And so notice, this doesn't depend on the mass of the satellite at all. It only depends on the radius, and it's inversely proportional to the radius. So the smaller the radius is, the faster the speed will be. So we're looking for the satellite with the smallest radius, which would be B. Alrighty. Next we've got an asteroid is moving in an elliptic orbit with the sun at one focus as shown above, with which of the following quantities increases as the asteroid moves from point P in its orbit to point Q. So as we go from P, we're closer to the sun. We have a lower height. We have a faster velocity. We're going to a higher height and traveling with a lower velocity. So our speed doesn't increase. Our angular momentum stays constant, so it does not increase. Our kinetic energy does not increase because our speed decreases, but our height increases, so our potential energy, that does increase. So D is going to be our best choice for that one. Number 3, we've got a person weighing 800 newtons on Earth, travels to another planet with twice the mass and twice the radius of Earth. And we want to find out what their new weight is going to be. And so their original weight would be just some gmm over r squared. And then we want to find out their new weight would equal g times the mass was twice the mass. Yep. And our radius was twice the radius. And so we can simplify this. We'll square the 2 on the bottom and have the 2 up here that we can pull out. This is 2/4 times gmm over r squared, which is our original mass, right? That was our original weight. And so the original weight has been scaled by a factor of 2/4, or 1/2. So half of 800 newtons is 400 newtons. Good, good. Cool. I'm gonna grab a little bit of water here. So next we have a same type of a problem here. The only difference is we're now not scaling both by 2, but we're scaling the mass by 10 and the diameter by 2. And so we have the same gmm over r to start with, but now we'll look for a new f prime that will be for 1/10 of the mass and for twice the radius, half the radius. Because the diameter is halved, therefore the radius is half, because diameter is just 2 times the radius. And so yeah, so this will then be r over 2 squared, and we're squaring that. So again, we get the same weight comes out front here, but then we have our scalar here is 1/10 over 1/4, or 4/10, 40%. 40% of our acceleration would be 40% of 9.8, or 40% of 10 if we're going approximately, and we say most nearly. 40% of 10 is 4 meters per second. That is D. And we know that we're going to make that approximation instead of using 9.8 because none of our other options are closer. I guess for what it's worth, let's see what it would be in actuality, like a bit more of a precise version. It would be more like 3.92 meters per second. Does that show up on the thing? Okay, that's good. You can probably hear the popping, but yeah, at least you don't see all the tutoring opportunities that I'm currently ignoring because I want to help you guys all at once and for free. You're welcome. Yeah, anyway, so moving on to number 5, we've got a multiple correct one here. We have two spacecraft, spacecraft X and spacecraft Y, which are true statements about X and Y, given that spacecraft Y has twice the mass of spacecraft, spacecraft X has twice the mass of spacecraft Y. On Earth, X experiences twice the gravitational force that Y experiences. Yes, that would be true, because on Earth we can approximate gravity to m times g. They have the same g, but if mass doubles, then the force doubles. On the Moon, X has twice the weight of Y. Yeah, that should also be true. Again, we can approximate this down to the acceleration now would be a gmm over r squared, but the r squareds, like, these terms wouldn't change, and then the m gets doubled, so it would double that force. So that kind of rules out C and D, but let's just double check them. The weight of X on Earth will always be equal to the weight of Y on the Moon. No, that's not going to be true, because we could... there's only a specific ratio that would be true for, so that's not going to always be true. And it's, yeah, no, it's weirdly specific. That's not a general lemma. When both are in the same circular orbit, X has twice the centripetal acceleration of Y. No, that's not going to be true, because acceleration is proportional to v squared, or is equal to v squared over r. Does not have dependence on mass. So D is not true either. That's okay. Good. So that leaves our first choices, A and B, is correct. Good. Yeah, and then we were asked to just select 2, so that's good. That confirms our hypothesis. So next, we've got 2 spheres pictured above have equal densities and are subject only to their mutual gravitational attraction. Which of the following quantities must have the same magnitude for both spheres? So we don't expect acceleration to be the same, because both of which are going to be under the influence of a same force of gravity. Both will have some g times their mass times the mass of the other one over their radius squared. We saw this before with big M and little m, but it's mass 1 and mass 2 for just 2 objects. You can think of this either way. And then for the other guy, he has a force of his mass times the big mass over r squared. But look, it's the same equation. All we have is the change in the order of our masses being multiplied in the numerator. But multiplication is what's called commutative. We can commute these by changing their order without affecting the meaning of the equation. So we don't expect acceleration to be the same, because they're experiencing the same force. So same force, different mass, different acceleration. Different kinetic energy, or same kinetic energy? Probably not, right? Because that has to do with mass. This one has a much larger mass. Don't know what their velocities are, but it's still probably not. Displacement with the center mass? Definitely not. Because center of mass is going to be very close to this guy, very far from the little guy. Gravitational force, yes, we do expect that to be equal, conserved due to Newton's third law. These are third law pairs. Both are acting equally and opposite. I mean, we also just checked that out here, right? We wrote out both of their gravitational cases, and it turns out we can commute those. So it's fine. Cool. 7, we've got an object has some weight W when it is on the surface of a planet of radius r. What will be the gravitational force on the object after it has been moved to a distance 4r from the center of the planet? So if we move it a distance of 4r, we're basically doing like this operation again here, right? Only now it's we're scaling it up by 4r, and we know that that's going to show up on the bottom, but it's getting squared, so it's going to be 1/16. Good, yep. 8, a new planet is discovered that has twice Earth's mass and twice its radius. On the surface of this new planet, a person who weighs 500 newtons on Earth. Okay, this is literally the same problem. Like, exactly the same as 3. The only difference is it's 500 newtons instead of 800 newtons. But yes, if we double the mass and double the radius wins because the radius is squared. So we get a 2/4, we get a 1/2 relationship. They're going to weigh half what they do on Earth, which is 250 in this case. Next, we've got a simple pendulum and a mass hanging on a spring. Both have a period of 1 second when set to a small oscillatory motion on Earth. They're taken to planet X, which has the same diameter as Earth, but twice the mass. Which of the following statements is true about the periods of the two objects on planet X compared to the periods on Earth? So this is kind of neat. This is using simple harmonic motion. So we can define simple harmonic motion with an omega, right? An omega for mass on a spring would be the square root of k/m. And for a pendulum, this would be square root of g/L. Acceleration due to gravity divided by length. Now mass, this is an important metric because mass is invariant throughout the universe. It's a measure of how much matter is in an object. So us moving mass on a spring to a heavier planet doesn't affect its mass, therefore doesn't affect its omega, therefore does not affect its period. So the mass on the spring will stay the same. The pendulum, however, is affected by acceleration due to gravity. Now our acceleration due to gravity we can think of as being this gm/r² term, because we multiply it by little m to get g in the case of Earth when we use mass of Earth near the surface of Earth, so when r is close to the radius of Earth. When r changes too much, it gets too large, this approximation falls out and we have to use the full version here. But notice how this term here, this g, does depend on the mass. So doubling the mass doubles g. If we double g, we double our we double our frequency. If we increase our frequency, we're decreasing our period. Therefore, D is our best option because that is the period of the pendulum is shorter, decrease the period, but the period of the mass is the same. That's what we said also. This would be invariant. Very good. Any questions on any of that? I believe that was the last for our multiple choices. And so now we can take a look at our FRQs. So we're jumping back to circular motion. We do have a gravity FRQ buried in here. But we'll begin with the circular motion guy. And so we've got some box on the back of a truck. A box of mass m is held in place by friction, rides on the flatbed of a truck which is traveling with a constant speed v. The truck is on an unbanked circular roadway having a radius of curvature r. On the diagram provided above, clearly indicate and label all the forces acting on the box. Okay, let's use red for this. So we know that there's going to be a gravity force pulling us down. There's a normal force pulling us up. And then there's one more, because we would expect this box to just kind of fly out of the circle where there's no friction. The circle is going to be inducing a centripetal force. It's pulling us back radially inwards. That is our friction. So to label these again, we'll have Fn, Fg, Ff, and that'll be all. Yeah, that's our part A. Next, we are looking at it when it rides up on a bank. Find what condition must be satisfied by the coefficient of static friction mu between the box and the truck bed. Oh, sorry, so that's for part C is when we bank up. Okay, so this is just in general here. So we expect the friction force to be the centripetal force. So that must equal mv²/r. When we're on a flat surface, so hang on, let's track this back a little bit. We also expect our frictional force to be equal to mu times our normal force. Now our mu, this coefficient of friction, is what we're looking for. And so on a flat surface, we expect our normal force to equal our gravity force, or mg. Do we have our m? Oh yeah, we have a big M, don't we? Look at that, big M. Oh yeah, and that will be the mass for that. That's fine. So we can write our friction force is equal to mv²/r. That would be mu times our Fn, which we said was big Mg, is going to equal big M times V squared over R. Now we just want to get mu on its own. So we're just going to divide by M. It's going to cancel on both sides. And then we'll divide by G, which is going to go on the bottom, giving us mu has to equal V squared over GR. And I'm just gonna move that equal sign back a bit because it's kind of blending in and then it makes it look like a minus sign. I don't want to have any extra confusion just because I write a little bit sloppy. But yeah, this is going to be our condition that we want to impose on our mu here. Good. Any questions? Good, good. You guys are excellent students. Next, now we're looking at when the roadway would be banked. So we're now starting to tilt ourselves up above this original flat. I can't draw a straight line for the life of me, apparently. That's fine. And so we're now tilted. And so this changes our normal force. Okay, so we want to clearly label two forces acting on the box under these conditions. Oh, even if the truck bed is frictionless. Okay, so now the truck bed is frictionless. I was confused there because I was like, well, there'd be three forces, right? There'd be our normal force, our gravity force, and our friction force. But there's no friction force this time because we're told this is a frictionless surface. So that's our Fn, this is our Fg. Notice how they don't align with each other. This is like our inclined plane problem that we saw back on Wednesday. Wednesday? Thursday. Good. That's all we need for part C then. And D will say which, if either of the two forces acting on the box, is going to be greater in magnitude. Well, this is going to be Fg, and we can prove it because we expect Fg we can split into. Let's get a bigger diagram down here just so we can see it nice and clear. So if we have some Fn here. And some let's do this properly here. Fg will point straight down. We can do the trick that we like to do, where we break up Fg into components to align with the inclined plane. I actually thought they were going to make us do the part B again, but with an inclined plane, but they didn't. But we know then that this this y component would be equal to Fn. And this y component is related to the hypotenuse Fg by this angle theta. And so we can then get the sine, no, not the sine, that would be the cosine because this is adjacent. The cosine of theta would equal Fgy, our adjacent, over our hypotenuse, Fg. Giving us then Fgy is equal to Fg times the cosine of theta. Now cosine maxes out at 1, and so that's going to be when theta equals 0. So the maximum Fgy can be is when theta equals 0. That would be when we're on flat ground. We are not on flat ground. We know theta is non-zero, so we know cosine has to be less than 1. So Fgy is less than Fg. And if Fgy is less than Fg, but Fgy is equal to Fn, that tells us that Fn is less than Fg. Good. Any questions on any of that? Looks good. You guys pay great attention. You're really good listeners. Next we've got a ball attached to a string of length L swinging in a little horizontal circle, but we're swinging from like a fulcrum up here, it looks like. We've got a constant speed. String is making an angle theta with the vertical, and the tension, and T is the magnitude of the tension in the spring. Express your answers to the following in terms of the given quantities and the fundamental constants. They didn't tell us what quantities are given. That's fine. Okay, and so they don't ask us to find tension anywhere, so I assume tension would be, yeah, one of the given quantities we can use. So we're going to start with the vectors when it's in the position shown on the diagram. Cool. So we've got a tension force going up this way. We've got a gravity force coming down like this. And that's it. That's actually it. We can think about how these would include an x component and a y component. And that's going to be important later because this includes that angle theta up there. This is t, and this is fg. I would usually label this as like ft, but they already defined it as t, so I'm just going to stick with their definition. Yeah, and so next we want to come up with the mass of the ball. And so the mass is going to show up in our expression of Fg. And so we want to then take this to a Newton's second law, and we want to think about all the forces acting on this ball in the y direction. And so we've got, because we broke up our tension already into two components, into a y component and now an x component, we expect the y component to balance out with Fg, meaning if we have a positive Ty minus Fg, that means our mass times acceleration has to go to 0. If we add that through, that gives us tension in the y direction is equal to Fg, which we can then say is equal to our mass times gravity. There's our mass. We want to get mass out on its own. So to do that, we divide by g. Ty is equal to m. Then we divide that by g. And then we just want to get this tension in terms of our main tension, T. So our y component of tension, that is adjacent to this angle theta, so that's then going to equal T times the cosine of theta, again, still over T. There's going to be our m. Cool. Any questions on that so far? Looking good. All right. Next, we want to do the same thing, but now for the speed. And so the speed is going to relate the x component. Now, why the x component? Well, if we look back up at our main thing here, our x component is pointing this way. It's the force that's pointing radially inwards. The circle we're tracing out is on the bottom here, right? And so this is the circle we're traveling around. This is the components of the force that are pointing along the radius, accelerating us in to give us that centripetal motion. And so to do that, then we will say that our x component of our tension is equal to mv squared over r. We want to get v on its own, so let's just multiply by, but we also don't know r, so yeah, we'll still get v on its own, but we'll have to substitute some stuff as we go. So we divide by m, multiply by r, and take the square root, giving us, let's see, so we have our tx, we multiplied it by r, we divided it by m, and we took the square root. That being said, we have to plug in our values. All of these values actually need to be replaced with values up here. Our radius is going to be on this side here, opposite our angle theta to our hypotenuse of L. So that means the sine of theta, so r over L is going to be the sine of our theta here. This is our opposite over hypotenuse, giving us then that r equals L sine theta. We get the same relation up here for the t's. I mean, we already did the cosine one. We kind of then know the x has to be the sine. So we know t sine theta is equal to tx. Oh, look, there's going to be a sine squared. Look at that. And then we have a cosine theta there. And I kind of want to just leave it like that. So, okay, so let's rewrite the v here. This might be another one where we need to get more paper because I'm kind of writing this all over the place. Okay, so that's going to be, we have an L sine theta times a t sine theta. So I'm just going to put the t here and square the L. In fact, let's actually, we know this is going to equal v, but I'm just going to move it, scooch it back a little bit just to give us more space. And then we divide this by t cosine theta over g. Now this can simplify. We don't have to simplify it. We can leave this like this, and that's perfectly acceptable. For what it's worth, we'll just tweak it a little bit. We'll cancel out the t's, and we'll bring the g up top. Again, that could probably simplify even further. You could pull out a trig function there, but I don't really want to do that. And if I do that incorrectly, I lose all the points that I've earned here. It's really not worth it. But yeah, this is my velocity, and as simple as I'm willing to go. Good. So now that we have that, we want to determine the frequency of revolution of the ball. We can get that from the velocity, because velocity divided by our radius is equal to our angular frequency, which is equal to 2 pi times our regular frequency. So v over 2 pi r equals f, which in our case would be this guy from before, GL sine squared theta over cosine theta divided by 2 pi times our radius, which we said was L sine theta. And that definitely can simplify, but I'm not going to do it because we don't have to. Why would we bother? This is a timed test. This would be something that you have to be moving through, and it's a difficult test. You're earning points. You don't want to risk any of the points that you've earned during it. So this would be our process, and this is how we would get F, and we would just leave it like that. So now, suppose that the string breaks as the ball swings in its circular path. Qualitatively, describe the trajectory of the ball after the string breaks, but before it hits the ground. So the ball is going to move. I guess, is there space up here? Yeah, there's space up here. So we'll draw this guy out again. If the ball breaks, it's going to kind of move downwards, but it's going to keep going in its last tangential velocity direction. There's nothing that's going to curve it. That's not going to happen. So we expect this to then move in a straight line out tangentially, which I suppose I should write, shouldn't I? So we expect this to be a straight line out tangentially. Yeah, this is the current format here, writing on a nice digital pad here. Not super conducive for writing things out. And unfortunately, the software I'm using for the Google Jamboard isn't very well suited for a lot of typing either. There's much better Google softwares for typing. There's better non-Google softwares for typing also. But, Google's free, so thank you, Google, for powering our learning here. So I'm not going to look a gift horse in the mouth, if I'm using that term correctly. But yeah, so qualitatively though, this is going to be the trajectory we take. We stop following the circular motion and move in the direction of our tangential velocity. Good. And so I believe this is our last one now, and this is going to be a gravitational FRQ. How are we doing on time? Are we still streaming? Why can't I see the Oh, I see. It's undocked my chat. Okay, hang on. I'm just gonna do a quick little tinker here. Can I see that? Can you dock this window, please? There we go. Why won't you dock? Oh, goodness me. Okay, well, that's fine. The chat window doesn't want to behave itself, but we're making really good time. And this is going to be one of the shorter units here, so we can expect this stream to be a little bit shorter than the others. This unit itself actually only makes up 4 to 6% of the AP tests. But that being said, including the rotational motion unit, that then brings it up to 20%. But the rotational unit we're going to treat on its own with torque and angular momentum. We're going to save that for last. This is just going to be the centripetal motion relating tangential velocity to centripetal forces. Good. So for our last guy, we've got a gravitational problem. We've got some satellite of mass m is in an elliptical orbit around the Earth, which has mass me and radius re. The orbit varies from a closest approach of distance a, that's at this closest approach here. Here's our distance down there. Actually, I have something for this. Yeah. So at this point here is our distance. Yeah, I gotta start using these laser pointers more often. And then maximum distance out here at point B for our furthest approach, our distance is this lowercase b. Assume gravitational potential, the energy, assume at point A, the satellite is V naught. We will assume gravitational potential at that point is 0. When the masses are infinite distance apart. Okay, gotcha. And express our answers in terms of all these guys. So in terms of our major and minor axis, if we want to get all fancy about our elliptical terms here, that's just going to be our A and B. In terms of the mass of the satellite, mass of the Earth, radius of the Earth, and the initial velocity. That is velocity at point A. That's actually going to be our maximum velocity. Yeah, so we want to determine the total energy of the satellite when it's at A. That's going to be total energy is kinetic plus potential, which is going to be 1/2 mv naught squared. That's our kinetic piece. Plus our potential will be our mass. Yeah, we probably want to actually use our so we can use potential as mgh, right? That would be fine. But we can actually do one better with using the actual gravitation, like the big G gravity equation. And that's just going to be our big G gravity equation multiplied by r. So usually we'd have an r squared. We're going to multiply it by r to give it just r. And at this point, that radius is a. So this is going to be our total equation, or our total energy. This is in terms of all of our stuff. That's a little e. Yeah, and that looks good. We chose A instead of big RE because we want the distance between their centers of mass, which includes big RE, but also has this little height term here that we can't ignore. Good. What is the magnitude of the angular momentum of the satellite from the center of the Earth when it is at A? So angular momentum we can define as I times omega. Yeah, this isn't something we covered today, but that's fine. So our I, we can treat our satellite like a point-like mass. So the point-like mass for a moment of inertia is just going to be mass times our radius. Our radius here is a, so this will be ma squared. Sorry, mass times our radius squared, excuse me. So ma squared will be our moment of inertia. Our omega is going to equal, no, it's not right, an equals there, because that's not an equals. This is an equals. Omega is going to equal our velocity divided by our radius again. So we get, that's going to be V naught, in this context, V naught over A. And so our angular momentum at this time will equal, let's see, we've got M times V naught. Oh, not up there though. Just making all sorts of typos without even typing. And then we have a squared divided by a, which is just going to leave us with an a on the top. This is our angular momentum. Good. C, we've got determine the velocity of the satellite as it passes point B in its orbit. Okay, and there's a couple ways we can do this. I guess I like the method of using conservation of angular momentum. So we expect angular momentum to be constant at both times. So that means this initial angular momentum we had at point A is going to equal the angular momentum at point B. And that's going to equal, again, we have a point-like mass, but now it's a radius b squared away. That's our I, and we want to multiply this by an omega. This will be our new v times our distance b that we're at. Now this v is not equal to v naught because we expect this velocity to be different at this height. We expect it to be lower. And so we said this is equal to LA, so we set this equal to mv naught times A. Cancel our m's. Our velocity does not depend on our mass, which is nice. We can cancel one of these b's, and to get it on its own, we'll divide it by that, giving us v is equal to v naught times A over b. We know A is smaller than b. We know then, therefore, this velocity is lower than v naught. That's what we expected to, because this is the moment of highest potential energy, therefore the moment of lowest kinetic energy. Lowest kinetic energy, therefore smallest velocity. And this is smaller than our fastest time we have up at this region here. Good. Cool. And that's what we want for part C. Okay, now we're looking at a point where as we go down to point A, our rocket burns retrograde. And so the thruster then fires in the opposite direction of our motion to bring us down to a circular orbit. So now we are all at a radius A at every point around this orbit. Yeah, and we want to determine the speed for the rocket at this time. So that's just going to be using our centripetal motion, our force of gravity, our gmm over r squared, but our r is a squared, is going to equal our mv squared over r, which is mv squared over our r, which is an a at this point. So that cancels there. We can cancel the m, and we'll take the square root, giving us our velocity is equal to the square root of gm over a. We've seen this before. We saw this as square root of gm over r. This is exactly that same thing. The only difference is we plugged in a for our r because our radius is a. Good. And then the last part would be determine the work done by the rocket engine to affect this change. So that would be finding the change in potential energy that we've gone through. Let's see, how do we want to do that? I guess so we want to look for our new point B. No, probably not like that. Let's do it like, oh, excuse me. Yeah, come on. Settle down. There we go. So yeah, we went from a potential. So our work will define as our change in potential. This is going to be the change in potential at point B, right? Because this went in to like a circular, like a circle-y circle. Good. No questions so far. And so that is our final minus our initial. Our final is going to be at gm. Let's write that again, but nicely. gmm over a minus our initial, which was gmm over b. And we can actually leave it like this. That is fine. We could combine it a bit, though. So we can write this then as, is that going to cover up, is my face going to cover this? Let me check the stream here. Okay, yeah, we can fit this in under here. We can factor out the gmm and write this as 1 minus a over 1 minus b. And that looks a little bit better. And that is going to be the work done to change our potential energy to get us down to this nice circular orbit. Yay! Orbital mechanics. And so I think that's actually all we've got for today. Let's have a look. Yep, that's it. Well, thank you everybody for coming in and watching. I hope you guys learned something. Next time, we'll be checking out work, power, and energy. This is going to be a big one. This is the longest unit on the AP test. It's got the majority of the questions. It's also a very important idea just in physics. If you plan on taking a physics major when you go to college, you'll see this come up a lot. This is kind of the fundamentals that we use to derive a lot of stuff like quantum mechanics, or debatably even general relativity, although that's really esoteric. At this level, though, we're going to be working with work, power, and energy, and how we can use conservation of energy to solve problems much more efficiently than kinematics or dynamics would. Check us out at 314education.com. We should have links to all our stuff we're doing. We're also on Instagram. Check us out at 314education.com. If you are interested in private tutoring, we're offering $5 off your first session if you like us on Instagram, if you follow us on Instagram. Our next stream will be Thursday, 22nd, so this coming Thursday. This will be the halfway point, halfway from when we started to when the test comes. It's sneaking up on you guys, so this is a good time to kind of start getting things together, thinking about where you're at for the test, what do you want to practice, what do you need to study more. Yeah, and this will be 5 p.m. Pacific time again. Yeah, any questions? Looks like we're good. Well, thank you everybody for tuning in. And until the next time, you take care, keep safe, and I'll see you guys on Thursday. Alrighty. I think we're done. If I can find the button that